Welcome to Manasi Solutions. We will discuss some problems in the topic homeomorphism. So, homeomorphism two metric spaces xd and yd dash consider a function f from x to y, which is 1 1 on 2, and f and f inverse are continuous. ഇത്രയും കണ്ടീഷൻസ് സാറ്റിസ്ഫൈ ചെയ്യുന്ന ഫംഗ്ഷനാണ് നമ്മൾ ഹോമിയോമോർഫിസം എന്ന് പറയുന്നത്. ഇത്തരത്തിലൊരു ഹോമിയോമോർഫിസം എക്സിസ്റ്റ് ചെയ്യുന്നുണ്ടെങ്കിൽ ഈ രണ്ട് സ്പേസസ് ഹോമിയോമോർഫിക് ആണെന്നോ അല്ലെങ്കിൽ ടോപ്പോളജിക്കലി ഈക്വലന്റ് ആണോ എന്നോ പറയും. ഓക്കെ, സോ എ ഫംഗ്ഷൻ എഫ് ഫ്രം x to y which is 1 1 on 2 with the f and f inverse are continuous is called a homeomorphism. And here we are going to prove that the real number system R is homeomorphic to the open interval 0 1. For that, we need to find a homeomorphism from R to 0 1. Here I am considering these two spaces together with the usual metric. Now, consider the function f from R to open interval 0 1 such that f of x is equal to 1 by 1 plus e raised to minus x. Here, for each x in R, this function f of x is defined because the denominator is not 0 for any x and e raised to minus x is defined for all x in R, and e raised to minus x will not be equal to minus 1 for any real number x. So 1 plus e raised to minus x is not equal to 0, which implies f of x is defined on the whole real number system R. Now, we need to prove this is a 1 1 on 2 and continuous function from R to 0 1 with f inverse also continuous. Now consider this function here. F is 1 1 because if f of x1 equal to f of x2 for some x1 and x2 in R, then which implies f of x is equal to x1 equal to 1 by 1 plus e raised to minus x1. This is equal to 1 by 1 plus e raised to minus x2. And this implies 1 plus e raised to minus x2 is equal to 1 plus e raised to minus x1. So, e raised to minus x2 is equal to e raised to minus x1, which implies x1 minus x1 equal to minus x2 by taking logarithm on both sides. And this implies that x1 equal to x2. So, f of x1 equal to f of x2 implies that x1 equal to x2. Therefore, this function f is 1. Next, here f is a continuous function for each x in R because e raised to minus x is continuous for all x in R, and 1 plus e raised to minus x is also continuous for x in R, and for any x, 1 plus e raised to minus x is not equal to 0. Therefore, the reciprocal of this function, that is f of x is equal to 1 plus e raised to minus x, is continuous for all x in R. Therefore, this function is continuous on R. And this is a continuous 1-1 function from R. And when we look at the codomain, this is a continuous function. Also, e raised to x is an increasing function. and therefore e raised to minus x is a decreasing function. And 1 plus e raised to minus x is what? Which is also a decreasing function, and 1 by 1 plus e raised to minus x is that what? Which is a increasing function. So here the function f of x is a increasing function, which is 1 and what? It is a continuous function. So when we look at this limit at minus infinity and infinity, f of x tend to what? 0 if x tending to minus infinity, and if f of x tends to infinity, sorry, not infinity, tends to 1 if x tending to what? Infinity. Why? When we look at this limit, x tending to minus infinity implies that e raised to minus x tending to infinity. And so 1 plus e raised to minus x also tends to infinity by x tending to minus infinity. So the function f of x tends to 0 as x tends to minus infinity. If x tends to infinity, then e raised to minus x tends to 0. Therefore, 1 plus e raised to minus x tends to 1, which means f of x equal to 1 by 1 plus e raised to minus x tends to 1. So here we have this limit, and f is continuous 1 1 and increasing function, which means what? F is a onto function. And also here for each y in 0 1 there exists a x in R such that f of x is equal to y. And when we look at x, f of x is equal to 1 by 1 plus e raised to minus x, which is equal to y. So 1 by y is equal to what? 1 plus e raised to minus x, and which implies e raised to minus x is equal to 1 by y minus 1. So this is equal to 1 minus y by y. And by taking natural logarithm on both sides, we get minus x is equal to log of 1 minus y by y. And hence x is equal to minus log of 1 minus y by y. By taking minus 1 inside of logarithm, we will get log of y by 1 minus y. And here y by 1 minus y is not equal to 0 for any y in open 0 1, and also 1 minus y is not equal to 0 for any y in open 0. Also y by 1 minus y is greater than 0 for all y in open 0 1. So if we take f inverse of x is equal to log of x by 1 minus x, then this function f inverse is defined because f is 1 1 and onto, and f inverse of x is continuous also. Why? Here 1 by 1 minus x is continuous on open interval 0 1, and hence x by 1 minus x is continuous on open interval 0 1, and this is always greater than 0. So log of x by 1 minus x is continuous on open interval 0 1. Therefore f inverse is also continuous. Here f is 1 1 on to f is continuous, and f inverse is also continuous. Therefore the function that we defined here is a homeomorphism from R to open interval 0 1. Therefore, these two matrix spaces are homeomorphic or topologically equivalent. Suppose A, B be any open interval in real life, that is A, B is an open interval with A less than B, and consider the open interval 0, 1. These two are metric spaces together with the usual metric. We are going to prove that these two metric spaces are topologically equivalent or homeomorphic. So here we need to find a homeomorphism F from the open interval AB or what? Open interval 0, 1, open interval 0, 1 to open interval AB. For that, consider the function f from 0, 1 to open interval AB, which is defined by f of x is equal to b minus a into x plus a for all x belongs to open interval 0, 1. When we look at this function, f is 1. Why? If f of x1 equal to f of x2, if f of x1 equal to f of x2 for some x1, x2 in open interval 0, 1, then which implies here what is f of x1? B minus a x1 plus a, and this is equal to b minus a times x2 plus a. Here we can cancel plus a from both sides, and we will get b minus a x1 equal to b minus a x2. Here b not equal to a, therefore b minus a is a non-zero number, so we can cancel it from both sides. Then we will get x1 equal to x2. Here f of x1 equal to f of x2 implies that x1 equal to x2. Therefore, f is 1. Now we need to prove that this function is onto. For that, consider a point y from the open interval AB, and if there exists an x in 0, 1 such that f of x is equal to y, then it implies b minus a times x plus a is equal to y. Then which implies that b minus a x equal to y minus a, and here b minus a is a non-zero number, so x is equal to y minus a by b minus a. So if we choose x is equal to y minus a by b minus a, then f of x will be equal to y for any y in the open interval AB. So each point in the open interval AB has a pre-image in open interval 0, 1. We know that if y belongs to open interval AB, then y minus a by b minus a will be a point in 0, 1. So here x is equal to y minus a by b minus a belongs to open interval 0, 1 for all y in open interval AB. Therefore, f of x is equal to y for any y in open interval AB. There exists an x in 0, 1 such that f of x equal to y, which implies the function f is onto. We know that any function in this form is continuous, and its inverse is what? Its inverse is f inverse is equal to what? F inverse of x is equal to x minus a by b minus a is the inverse of this function. And when we look at inverse of this function, which is also in the form what? 1 by b minus a into x minus a by b minus a. So all functions in this forms are continuous. So f inverse also continuous here. Hence, the function that we defined from open interval 0, 1 to open interval AB is 1, 1 is on to f is continuous and f inverse is continuous. Therefore, this function is a homeomorphism from open interval 0, 1 to open interval AB. So, for any open interval AB with A less than B, we know that from this proof we can say that which is always homeomorphic to the open interval 0, 1. And from this we can say one more thing. Here any open interval AB is homeomorphic to what? Open interval 0, 1. And open interval 0, 1 is homeomorphic to what? Real number system. So we can say that any open interval AB is homeomorphic to what? Open interval open interval AB is homeomorphic to real line, the whole real line for any open interval AB with A less than B. And one more thing is here, when we consider two different open intervals, A1, A1, B1, A2, B2. Here we know that A1, B1 is homeomorphic to 0, 1. And 0, 1 is homeomorphic to A2, B2. Therefore, A1, the open interval A1, B1 is homeomorphic to open interval A2, B2. So, any different open intervals in R is homeomorphic to each other. Okay. We are going to prove that the open interval A infinity is homeomorphic to the real line R for any real number A. To prove this, we need a homeomorphism from the open interval A infinity to R. So, consider the function f of x is equal to natural logarithm of x minus a. Here, the open interval A infinity and R are considering with the usual metric. Now, consider the function f of x is equal to natural logarithm of x minus a. We know that this function f of x is defined for all points in R. Why? The natural logarithm is defined for all positive real numbers. And here x minus a is greater than 0 for all x in the open interval a infinity. Therefore, this expression x minus a is positive for all x in this open interval, and hence f of x is equal to natural logarithm of this x minus a is defined for all points in the open interval AB. Now, we know that natural logarithm is a increasing function and x minus a is also an increasing function. Therefore, f of x is an increasing function on open interval a infinity. And f of x is continuous. Why? Why f of x is continuous? We know that h of x is equal to x minus a is continuous for all points in what? A infinity. And natural logarithm is also continuous, natural logarithm of x. If g of x is equal to ln of x, then which is continuous for all positive numbers in open interval 0 infinity. Therefore, we can say that f of x is equal to composition of these two functions, g composition h of x, which means natural logarithm of x minus a. is continuous for all x in open interval a infinity. And from this we can say that f is a one-one function. F is continuously increasing function. Therefore, f is a one-one function. But we can prove that f is one-one by taking f of x1 equal to f of x2 implies x1 equal to x2. Before that, we are going to find what is the range of this function. We need to verify what is the range of this function. Now, f is continuous and increasing function, and as x tending to a, x minus a tends to 0. So, ln of x minus a tends to minus infinity. And as x tending to infinity, x minus a tends to infinity. And therefore, ln natural logarithm of x minus a tends to infinity. So, this is a increasing continuous function, and as x tends to infinity, ln of f of x tends to minus infinity, and as x tending to infinity, f of x tends to infinity, which means that what? Which means the range of f is the whole space R. So the function, the range of this function is R. And but we need to find what is the inverse of this function, and we need to verify if this function is 1 by taking f of x1 equal to f of x2 implies x1 equal to x2. So f is 1. For that, if there exist points x1, x2 such that f of x1 equal to f of x2, then which implies natural logarithm of x minus a, x1 minus a equal to natural logarithm of x2 minus a. By taking exponential on both sides, we will get x1 minus a is equal to x2 minus a, which implies what? X1 equal to x2. So, the function f is 1. Now, f is onto. So, for each y belongs to R, there exists an x belongs to a infinity, such that f of x is equal to 1. And f of x is equal to natural logarithm of x minus a, which is equal to 1, which implies x minus a is equal to e raised to 1. And this implies that x is equal to a plus e raised to y. So, the inverse image of y is a plus e raised to y. So, f inverse of x is equal to what? A plus e raised to x for x belongs to R, and f inverse is a function from R to open interval a infinity, and therefore by looking at f inverse x, we can say that here e raised to x is a continuous function. Therefore, a plus e raised to x is a continuous function, which means this function f inverse is also continuous. So, the function that we defined here is continuous 1, 1 on 2, and also we have what? F inverse is continuous. Therefore, the function is a homeomorphism, which implies what? Any interval of this form is homeomorphic to R. By taking f of x is equal to minus of logarithm of what? Logarithm of a minus x, we can say that the interval minus infinity a is homeomorphic to the whole real line R. Here f is a function. This function is defining from the open interval minus infinity a to r. So this function is a homeomorphism from minus infinity a to r. So these two spaces are homeomorphic. Here we considering these two spaces together with the usual metric. So in general, what are the things when we consider the open intervals in R? What are the possibilities? Either it will be in the form minus infinity a, or it will be in the form AB, where a and b are finite numbers, or it will be in the form a infinity. These are the only open intervals in R. And we proved that any open interval AB is homeomorphic to R at first, and then we proved that a infinity is homeomorphic to R, and now we have minus infinity is homeomorphic to R, which means any open interval in R is homeomorphic to R. Okay.